Okay, so we continue with the second part of chapter 2.
Yeah, so the full chapter was about the construction of the Brownian motion. We already saw what the definition of Brownian motion and how we can get a continuity out of the sample paths. Now we are just going to focus on the properties of these sample paths, and we'll extend the Markov property we already have of the independence of these increments between each step, right? So, quick reminder, that was the last definition we saw, and right after this, there is something I didn't include in the presentation, that the winner measure. It's defined by, so the winner measure of that, well, is a measure in this space of the continuous function that goes from the non-negative real numbers to the real numbers. It's defined just by the measure of A will be the probability of B dot belongs to A, where this B dot is the mapping that gives us, well, that we give a T, and it gives us back a realization of the Brownian motion at the time t. Okay. This is, like, briefly explained it. It doesn't, like, it goes on for like 2 pages, but it doesn't use a lot of this in the chapter itself. But it gives us a property that we'll use, and it's that if one Brownian motion, if a property holds for some Brownian motion, it will also hold for a different Brownian motion, for any different Brownian motion. So this is something that we'll want to use in some proof in the chapter.
I mean, that means that all Brownian motions have the same law? Is that what it's saying? Or?
Yeah, it's just, so the property holds for with the same probability follow. Okay, so the very first law that we have in this section is the elemental 0-1 law, and it says that the sigma field F0. Sorry, I forgot to read this also, in which we will have that. The is the sigma algebra of of S, which is less equal T, and G dot F0 plus would be the intersection of S greater to 0 of the sigma algebras. I think that's it's that. So in the sigma field F0 plus, this one is trivial in the sense that every event has either probability 0 or 1. Okay, so the proof of that is we check the his idea of independence, that if we have, for example, x times I, this will is independent if this holds. So the events we are going to use, in particular, we're going to call A to some set or subset, subset in F0 plus, and we'll have G bounded and continuous function, and we'll see the expectation of this value. So for some random time steps G sub G1 to G sub n. Okay, so in particular, in here I cannot just separate them because this it's in F0, so it's kind of some initial conditions of the Brownian motion we have, and therefore this will somehow depend on that. But we'll use the continuity of G to say that this expected value is going to be equal to the limit when epsilon goes to 0 of the expected value of this
That's by dominated convergence.
Yeah, because
D you bounded by its infinity norm.
Yeah.
Okay.
And right, and since this is going to be 0, right?
They will be convergent to 0. You're right, right? Because they're continuous.
And now, thanks to the Markov property we have for Brownian motion, all of these increments are going to be independent of the of this f. Right? Therefore, this is going to be independent of this, and we can just exploit this and get that since this doesn't depend on the epsilon, we'll have this is expected.
You're using the Markov property there, right? That
Yeah,
this
in
BT1 minus
this,
epsilon is like a Brownian motion which is independent from Brownian motion up to time epsilon, right?
Yeah. Right, so I can split this and times the limit of epsilon therefore, we have this is the
There's the probability.
There will be just the probability of A, and this. Sorry,
The expectation.
Here. And now, since we have the convergence.
Dominated convergence.
Yeah, but I can switch the expected value with the limit. Then I'll have the limit inside, and we'll have just the expected value of the original value. So G1, G2, and so forth. To Gn. And then we have the independence we want. In this case, I was in fact doubting a little bit why we use the indicatrix, but I think it's because it allows us to build any upper measurable function.
Right. You will use first like non-negative by just adding these things, and then you can take anything. But okay, so you get the independence of these two, like you get the independence of F0 plus.
Yeah.
With the Brownian motion, right?
Yeah.
I mean, this is basic, but why does this imply the fact that you have only 0 and 1 probabilities?
Yeah, so what we have here is that F0, right, will be F0 plus will be independent of the events in here that will be any, and therefore will be independent of any sigma algebra of B sub t for t related to 0. That is the case that we took in here.
Right.
But
you will
states you'll have that this with
you intersect
the
those.
limit of
right.
This.
This is a decreasing limit of.
So it's going to be also independent with itself.
Then you have it.
Yeah. So that's the proof of the theorem. After that, we have this proposition that we have almost surely that for every epsilon relative to 0, the supremum of E sub s is going to be positive and the infimum is going to be negative. And a second proposition that for every real number, we have that the time it takes for the Brownian motion to hit that value is going to be almost surely not infinite. So, and well, after that we have the lim sub and the lim in. So. Okay, so just to let's prove the proposition number 1. Right, so in here we'll use a sequence of epsilons such that it's decreasing. So like that. And we call event A the intersection of B of the supremum of B sub S between 0 and epsilon B being greater than 0. Okay, so since this is a intersection, and what we have here, therefore it's easy to see that A is going to be inside of F0 plus, right? And in particular, we'll use a previous law to see that this the probability of this is greater than 1/2, and therefore it's going to have to be 1. So we have that the probability A, it's going to be the limit that equals to infinity of supremum right there equal to 0.
Shouldn't this be the limit of p going to 0 rather than infinity? Or
No,
not?
no, because the epsilon goes to 0. This is the
sorry. Epsilon p is a sequence. Okay. I
Yeah,
see.
the sequence is of epsilon p is
Sorry.
decreasing.
Yeah, got it. But where's the probability there?
I think, yeah.
It's
It's
okay.
Yeah, thank you. And we have for that, and sorry, it was equal, and up there was equal. Yeah. And therefore this point is going to be right there equal to just the limit c goes to infinity of probability of e sub epsilon sub p being greater equal to 0, and since that's right, yeah,
That's 1/2, right?
yeah, and since this is just symmetric Brownian Gaussian, it's going to be a half. And therefore it follows from the fundamental law that this has to be 1. Right? And the same idea with the other side, when we want to see that the infimum is going to be negative, we just have the same argument, but we can take minus p and it still is some Brownian motion. We have the same idea. Okay. And for the second one, so So the second one, we want to show that for every a in the real numbers, the t sub a, and that t sub a, naturally for every a in the real numbers, the t sub a is finite, right? So we'll here they write this, so we have that this is the probability of the supremum being right there equal to 0. That is just what we have from the first proposition. And they also write that this is the limit when delta goes to 0 of probability of the supremum being greater than this delta, or as in that. Right, so what we using here is also a proposition we have for the second subsection here, that if we have a Brownian motion, right? We sorry, viscosity, we can scale this and have that 1 divided by lambda lambda squared t, I think. I think
also,
it's also Brownian motion. It's also a Brownian motion. So,
but the second equality is not obvious to me. That one. You say
yeah.
it's the limit. Wait.
Yeah.
Oh,
where
you're
this
only
is
okay. I thought
yeah.
that below you're using delta or something, but it's not. Okay, I see. No, it's obvious. It's obvious.
Okay.
Sorry.
Okay. So now what it says is that it looks to this probability that the supremum of t is greater than delta 0 s and 1. But this is the same that we scale this by the probability that a new Brownian motion that they call the delta of s with s in between 0 and in here it should be 1 divided by 1 divided by delta squared separated from delta. Right? Sorry, and 1. Yeah.
So BS delta is another Brownian motion, but
Yeah.
it doesn't matter.
Yeah, it doesn't matter because it just escalated with respect to this delta. So the property we already have. And also, thanks to what the book says in the winner measure, is that we have that since this probability, the probability of this holding for this Brownian motion will be the same for any other Brownian motion. So instead of that, we can just change this for the original one, and this is going to be this. Without the delta. That's what they do. Right. Yeah. So and of course, since it's the same probability, we'll have this is going to be just 1. So in this case, that the probability that the supremum is higher than 1 is going to be 1. Therefore, since this is continuous and it starts at 0, we have to go through 1 in some points. And also, with the same idea of the scaling this, we have that we can change this 1 by any other thing, right? So that gives us at least the first part of the second proposition. And the other two just follow. I think they follow pretty easy from that, right? And the limit and the limit.
I mean, you can start stacking together these events, right? Like there's going to be a finite time where you hit 1, and then from that you have another Brownian motion, you hit 2. Is that okay?
Maybe put the limit inside, because we have the limit of delta going to 0, and then the supremum will be taken. I'm just.
I mean, okay, but I mean it's clear, one way or another.
Okay, more positions. I think I'll try to go just fast in here so we end the chapter. And okay, first corollary. Almost surely the function that gives us the Brownian motion. It's not monotone and on any non-trivial interval, so that's just really direct from there, from the first proposition, right? So we can take any interval, it's going to be positive or negative. I'm not sure why. And a second proposition that, so if we have T0 equal to 0 and that follows sequence with a mesh that tends to 0, so the max, we have that, oh, sorry, thing is the prime of the C sub n minus D sub n minus 1 goes to 0, I think it's something like that.
Yeah.
Therefore, we'll have this. And it's something that comes right from the something we proved for the first chapter. Because we can write this just like Gaussian eyes, and we'll have that limit straightforward from the theorem. And with that, we'll have also that almost surely the function that gives us the Brownian motion has infinite variation on any non-trivial interval. So that's also, I'll write that because it's going to happen fast. So just to remember the variation, it's defined as the sum of E of equals to 1 with I minus f E sub I minus 1 over any over all the points of the sequence, right? And in this case, we'll have that this sums holds that Brownian motion at time t sub I n minus the Brownian motion at time t y minus 1 squared, right? And here the n just tells us that we are using some particular mesh. It's going to be less or equal that the sum, the supremum of 1 was equal to y was equal to p of e sub t and sub I minus e sub t I minus 1 yeah, and this times, right, just the same sum. So this is going to be t n y I and b sub t I minus 1 n absolute value, right? This, since we are just like taking the same value and the supremum, like the greater one. But what we have from the previous theorem is that this tends to as sorry, since this goes to infinity, this tends to t. right? And this primum, the difference as this is going to be as n goes to infinity, this is going to 0. Since the time steps are always smaller, we'll have that this must be infinity, right? And which is the variation of the Brownian motion, right? Everything okay? So that's the subsection, and now we go with generalization of the strong property. So we'll define, first of all, some things. We'll define a stopping time. Okay, there should be an S, but a stopping time if for every t greater or equal to 0, we have that the event of the stopping time, like the event we want to happen happens before t, depends only in the history we already have seen, right? And here there is just a generalization of this.
So, I mean, you can conclude from the first one that also the event t is strictly less than t.
Yeah.
Yes. Is
Sure, like the
ft
same.
measurable.
And I'm not 100% sure of why exactly. I think it does this for using the dyadics in some other proof, but
I mean, I think, first of all, it's not obvious, right? That if you have that kind of measurability, you also have this one. But, so he's just making the point that it is the case. I'm sure in some proofs it's necessary to have either.
I think it's like a technicality because sigma algebra isn't closed under non-numerable like intersections and unions, so we have to reduce it to the case of numerable.
Yeah, that's true. But I think we've been doing this all like throughout the day, right?
Yeah.
Because all these
Time.
supremum and like all these things have to be taking over countable
Oh yeah.
sets.
and if we have t a certain time, sigma field of the past before t is going to be just this, right? Where f sub infinity is going to be the sigma algebra of just sub s for every s. And of course the book gives some examples of this. So, for example, giving t to be the moment in which we hit some specific value, it's going to be a stopping time. But for example, the event of having the I don't know.
I think the example from the book is like the last time Brownian motion hits a certain value.
Yeah.
That's not a stopping time because you never know when it's going to be happening again.
And here's the strong marker property. So let G be a stopping time, we assume now that the probability of that stopping time being finite is going to be greater than 0, and we set for every t this. Then under this probability measure, this is also going to be a Brownian motion, independent of s of t, right? And this proof is kind of really long, so I don't know if we shall I
Maybe we can
continue with the
Yeah, I guess it's homework.
okay. And from that we also have some few theorems. The first one that for every positive t, if we have S of t as the supremum of the Brownian motion until the moment t. If a is also a positive number, with this b, we have that the probability of the supremum being greater than a and the probability, and b being less or equal to that b is going to be this. And well, that comes directly, kind of directly from the Markov principle, I think.
But that last
Nice.
conclusion, it's not so obvious to me. That ST has the same distribution as the absolute value of BT.
Yeah,
Do you, I guess,
I'm not sure.
do you maybe take what?
Okay, so for that part, yeah, what it does is that kind of calculates the density of theta.
Ah, okay. So it uses this formula to.
Yeah.
Okay.
I mean, yeah, it's not like that straightforward as I said. I forgot about a little bit about that. Okay. And some corollary that also comes from that is that for every positive a, the t sub a has the same distribution as the and has this density in here. With this where, well, I don't think I defined that, but t sub a being the
Is a hitting time, right?
yeah,
The first time you get
so
BT equals A.
would be int of as such that it's equal to a, I think. I think that's and it also extends this to some other cases because up to now we have just worked with center Brownian motion, something that starts at 0. It's also something we can extend to starting any real number with this, so we would call real Brownian motion a Brownian random process that can be divided in a Brownian motion and some C that is they are independent, and a d-dimensional Brownian motion, something that is a Brownian motion in each component. And also they give from this a combination, and we have a real d-dimensional Brownian motion, but again, same idea. Now each component can be divided in this idea. So we have a C that doesn't depend on B, and a Brownian motion for the component that also doesn't depend on any C. Okay, and well, I think that's
That's it.
that's it.
Ah.
I think, yeah, that's kind of
Okay. Any? So there's no proof you want to include now that you have some extra time, or?
I don't know which one we go.
I mean, this TA is short, right? Do you?
Which
No, the next one. That one is pretty short. Like.
okay, so the proof of
This,
it.
I think these kind of things are useful.
what does doing here is that we want to find the density of T sub A. So we have that the probability of T sub A being lesser A being lesser or equal to some T. It's going to be what the probability of T being equal to A, or to in order to use the previous theorem, right?
Right. I guess,
So-
yeah.
The probability of this being
This is going to be the absolute value of Brownian motion at t greater than or equal to a.
So absolute value of this.
Right. And then they say, okay, bt squared has the same law as t times b1 squared.
Sorry, can you repeat?
bt is, oh sorry, u squared is this thing, right? So
Okay, so u square.
no, you squared both sides of the inequality and you're
Ah,
not doing
okay.
anything,
Yeah.
and you basically get rid of this absolute
Yeah.
value by doing that. And then you say, okay, bt squared, right? It's just the same as t times b1 squared.
Probability of times
b1 squared.
1 squared.
I mean, here we're just looking at a marginal of the Brownian motion, right? So this is just a normal, and you could say, like the
Yeah,
law
yeah.
of bt is just, yeah. And then, yeah, you just rearrange and you get this, is that event is exactly equal to, yeah, it's
Yeah.
a squared over b1 squared at most t. b1 squared. So yeah, I guess that you
Yeah,
conclude that
right.
these two random variables have the same distribution. The formula, I guess, it just follows from integrating this thing. You do know that this is a normal, so,
Yeah.
but yeah. Okay, thanks a lot. With this, we conclude chapter 2. So thanks, Gustavo. And next time, Matias, right?
Yes.
Yeah. Okay.
I have a question about the